Here we want to show that the covariance between x and y is equal to the expected value of xy minus the expected value of x times the expected value of y. So before we begin, let's review a couple of things. We'll call this lemma 1 or fact number 1, that the expected value of k times x where k is some constant and x is a random variable is equal to k times the expected value of x. So what this means, and you can prove this if you'd like, but what this means is if we know what the expected value for a particular set of data is, then scaling that data, right, multiplying each data point by 1,000 or dividing it by 3 or whatever, scaling that data keeps the same expected value, just scaled by that amount. Okay, and that makes a lot of sense if you think about it in terms of data. Next, we'll call it lemma 2. The expected value of f of x plus g of x is equal to the expected value of f of x plus the expected value of g of x. And again, the linearity property is in your book, or you can prove that yourself. But I'm going to use both of these facts as we go through this proof. Okay, so let me begin by saying let the expected value of x be mu x, okay, and the expected value for y be mu y. Okay. Then the covariance of x and y by definition is equal to the expected value of x minus the expected value of x times y minus the expected value for y. So that's just the definition of covariance. Now, if we look inside that expected value bracket, we've got x times y minus the expected value of x times y minus x times the expected value of y plus the expected value of x times the expected value of y. And again, all we did was we opened up our brackets and made this a term-by-term sum rather than a product. Now, by our linearity property, the expected value of a sum by lemma 2 is equal to the sum of the expected values. So this should be equal to the expected value of xy minus the expected value of the expected value of x times y minus the expected value of x times the expected value of y plus the expected value of the expected value of x times the expected value of y. Couple of things though. We can rewrite the expected value of x as mu x and the expected value of y as mu y, and those are constants. So we've got the expected value of xy minus the expected value of mu x times y minus the expected value of mu y times x plus the expected value of mu x mu y. But of course, because those are constants, we can bring them out front of our expected values. So this is the expected value of xy minus mu x times the expected value of y minus mu y, the expected value of x, plus mu x mu y times the expected value of 1, which is 1. And of course, we can change this expected value of y to mu y, this one to mu x. So this is the expected value of x and y minus mu x mu y minus mu y mu x plus mu x mu y. And these two cancel each other out, or any of those cancel each other out really. So if we switch these guys back to the expected value of x and expected value of y, we've got the expected value of xy minus the expected value of x times the expected value of y. And so we've shown that the covariance is in fact given by that formula. We used lemma 1 here. Sorry, lemma 2. And we used lemma 1 when we took these expected values, these constants, the mu's, outside of the expected value. Okay, so we used both of our lemmas. We needed to use both of our lemmas in order to prove this.